Here with us Dave Forney, who many of us know for many years. Dave has been a very distinguished researcher in information theory. He was involved from 65 to 99 with Codex, which then became part of Motorola. He has been very much involved in information theory, both as in the section as a president of the Information Theory Society. He's a member of the National Academy of Engineering, National Academy of Sciences, and the American Academy of Arts and Sciences. He has received some of the most prestigious awards, including the IEEE Edison Medal in '92 and the '95 IEEE Claude Shannon Medal. Today, he will talk to us about codes and graphs, and he is currently an adjunct professor at MIT.
Thank you, John. I appreciate the invitation and the introduction. It's nice to see so many people here today. I am going to talk to you this morning about research that I've been conducting over the past couple of years, really in my retirement, and that continues a line of research that I've been on for a long time, the algebraic structure of codes, especially in terms of their system theory, dynamical properties. But at this advanced stage, I decided the time was right to go back and try to redevelop the theory from the most fundamental level. And that's what I'm going to try to communicate to you today. I want to acknowledge that I've been collaborating in recent years with Heidi Glusing-Lursen, and she's contributed to a lot of these results. So we're talking about codes. The kinds of codes we're talking about are the ones used in data communications to approach Shannon's channel capacity. For this application in practice, we always use codes with a linear property or sometimes just with a group property. For various reasons, it doesn't cost us anything. It very much simplifies the analysis as well as the actual implementation of coding and decoding. There's a lovely symmetry property whenever you have a group property. On power limited channels where we use binary codes, we're always talking about linear codes there. On bandwidth limited channels, we generally go to multi-level codes, which typically have a group structure rather than a bit linear structure. The codes that are used in practice, we find very often have an underlying graphical structure. At a very early stage, people saw the advantages of convolutional codes, later generalized for the Euclidean space channel to trellis codes. I don't know what range of backgrounds we have in the audience, so I'm not going to go any deeper in any of this, but these codes have the structure of a dynamical system, a state-space dynamical system, which in coding theory we call a trellis structure, and they're sometimes represented by a trellis diagram. More recently, in the last 15, 20 years, there's been an advent of new classes of codes that can actually approach capacity. Low-density parity check codes, which are based on bipartite graphs, which represent the parity check structure of a linear code, binary linear code. And one of the things I have in mind here is that whenever we have a graphical structure, it leads directly to a decoding algorithm. It gives us a recipe for a decoding algorithm for that code in terms of standard things like sum product decoding, also known as belief propagation. You just apply it to the graph. And so when you have a graphical representation, it gives you a first step to decoding the code. So what I want to do is develop the fundamental algebraic system theory of linear or group codes defined on a graph. Please interrupt me at any point, particularly at these early points. So I want as many people to stay with me as far as possible. So if you have any questions, I'm happy to interrupt. All right, so let's talk about a graphical realization of codes. First of all, let's just talk about a realization in system theory terms, and I'm going to be talking in terms that are very much those of behavioral system theory of Jan Willems and other people. So what we really have is just a system of variables and constraints. The variables can be either the external variables, which in our case would be the actual code symbols, the ones that actually go out to the channel, and then there are internal variables, often called state variables, that we, the designers of the code, introduce for some purpose, usually to make things nicer. We're going to assume always that everything is finite or finite dimensional whenever we need so to. We're not going to get into any mathematical complexities from infinities, and that everything has a linear or group structure. And what do I mean by that? I mean that our variables are going to be themselves either vector spaces over some field, a binary field, for instance, or they're going to be groups, specifically finite abelian groups, the simplest kind of groups. So we're going to be talking in terms of symbol configurations A and state configurations S. We're going to have a set of constraints on these variables. The constraints themselves will be determined by codes. For instance, a set of 3 variables might be set to be equal to one another. That would be a very simple kind of constraint, an equality constraint. So each constraint, first of all, itself is going to be a linear or a group code on the variables that it involves, and that's what's going to tell us what the constraint is. If it's an equality constraint, that's just a repetition code. They all have to be equal. And each constraint is going to involve just a subset of all of the variables we've defined in our system. Okay, and that's what's going to determine our graph. From a realization point of view, the overall behavior of the system is the set of all configurations of state and symbol variables that satisfy all the constraints. Okay, once we've defined our constraints, this defines some subset of the set of all possible configurations that is valid. And that's our behavior. The code that's realized is just the projection of this onto the external variables, onto the symbol variables. So it's the set of symbol variables that occur in some valid state symbol combination. Okay?
So at this stage, there's no memory interpretation of the state.
There's no time in this. If we want, we can identify some of the indices with time, but we don't have to. Okay?
Even if you identify with time.
Our time axis can be replaced by a graph. That's where we're going.
Even there, you don't necessarily have to have a memory interpretation of the state.
No, it's just starting.
That's some variables.
Most basic level. I told you I'm going back to first principles. Right. Okay, now I'm going to impose some requirements here that are going to seem to you rather stringent, but in fact are not at all. I'm going to require that each symbol variable be involved in only one constraint. Okay, that seems like a rather strict thing. So I know the constraint that every symbol variable goes into, and each state variable be involved in only 2 constraints, precisely 2. There's no point in having state variables that are involved in just one constraint. Now that seems strict, but in fact it's 2-line proof to show that any realization, starting from any realization, I can normalize it just by inserting equality constraints, trivially. And it doesn't change the structure of the graph I'm talking about in any essential way. So there's really no loss of generality if we make this restriction. We're only going to talk about normal realizations, namely realizations satisfying these 2 properties. And once I've done that, there's a clear translation from a realization to a graphical model for the realization. We make the constraints correspond to the vertices in the graph. The symbol variables, which only touch one constraint or one vertex, those are going to be half edges. All right? And the state variables, which touch 2 constraints, are going to be the edges. All right? So, pretty basic.
What do you mean by half edge?
A half edge is an edge that only touches one vertex. It's an edge of degree 1. This makes it into some kind of hypergraph. if you want to be technical about it, but I think it's intuitively obvious. All right, a normal graph then, as I've already said, leads immediately to a decoding algorithm, specifically a so-called sum product or belief propagation decoding algorithm. And one of the earliest results is that on a cycle-free graph, if you apply this algorithm, it turns out to have a finite number of steps and give you an exact answer. But if you apply it to a graph with cycles, the algorithm becomes an iterative, approximate algorithm that may or may not converge, needs some kind of stopping rule, etc. If any of you are familiar with belief propagation or sum product decoding, you know about these things. So there's a big distinction between the cycle-free world and the world of graphs with cycles. Okay, give you some examples. Trellis realization has a sequential chain graph corresponding to a time axis, which in our case is a finite time axis. For normal linear time invariant systems, we want to talk about an infinite time axis. 2412 Golay code, any of you who've taken coding theory know this is one of the most famous codes with extraordinary algebraic structures, so it's a good thing to look at. People spent a lot of time, this is called a trellis realization of a code in general. The constraints in this case correspond to, well, external variables are indicated by this little dongle symbol here. You can see each of the external variables here only touches one constraint. Internal variables are states connect two constraints, and so sometimes people say what's distinctive about Forney graphs or normal graphs is that the states go with the edge, the variables go on the edges, and the constraints go in the vertices. The variables going on the edges is what's different from most graphical representations. So the states are communications between the constraints. The constraints involve, what do they constrain? They constrain the set of all states at time 1, symbols at time 1, and next states at time 2. So this basically tells us the set of all state transitions that are possible and the set of symbols that go with them. Yes?
Is there any directionality in these graphs, or these graphs?
There's no directionality, right? So these are this is not directed graphs, and that's a characteristic of behavioral system theory that I'll talk about in a minute. Sasha?
Is it possible to connect this picture to a slightly more familiar to me language of message symbols and parity checks? Where do we see the 12 message symbols and where are the parity checks here?
I'll show you that when I show you a graph of an LDPC code. All right, so wait through 3 slides, I think.
Not direct is bad, so, but use the word next.
I'm trying to relate it to a classical time axis.
Next to S1 or not?
Well, you know, I still have an index set where 2 is greater than 1, so that's the only sense in which it's next. I'm trying to relate it to classical state space systems. All right, for the Golay code, I'm actually taking the symbols 4 bits at a time. So each of these symbol spaces is Z2 to the 4th. There are 6 of them, so that gives us 24 bits. The size of the state spaces, they're all binary vector spaces. The first and 5th ones are of dimension 4. The second and 4th ones are of dimension 6. And the middle one is of dimension 8, which means there are 256 states in the middle of this trellis representation. And this, by the way, is known to be the most efficient trellis representation possible for the Golay code. The constraints, therefore, they're all self-dual block codes, and these are their parameters. The 2 in the middle have parameters 18, 9. That means they have 512 code words of length 9, the 9 being the 4 input bits, the 6 bits in the center state, and the 8 bits in the center state, and the and the 6 bits to one side. All right, so we say this is a 256 state trellis representation of the Golay code because the largest state space has size 256. For decoding complexity, it's a better measure is the branch complexity, which is the largest size of any constraint code, and that's 512. And it's known that you cannot improve on that with a trellis representation. All right, here's another non-trellis but still cycle-free representation of this same code. Here we take the bits 8 at a time. We constrain each of these 8 down to a state space of size 6. So none of the state spaces here is larger than 64. This is a 64 state cycle-free graph realization of the Golay code. But notice that the maximum constraint code size here, which is the size of the constraint in the center, is only 512. It's still only 512. And I'm not sure there's ever been a proof, but it's pretty well accepted that you can't get a cycle-free representation of the Golay code that has constraint complexity less than 2 to the 9th, 512. All right. But can we do better by going to a cyclic representation, some graph that has a cycle in it? And yes, we can. This is a so-called tail-biting trellis realization of the same code, the Golay code, on a graph which is a single cycle, the simplest possible cyclic graph. And if you're willing to accept a cycle in your graph, otherwise the structure of this is like a trellis, 12 successive times if you like, but now we take inputs 2 bits at a time, and all the state spaces are size 16. All the constraints are of size 32, so we get considerably simpler transitions, trellis sections. It's just from a 16 state to a 16 state. There is a 2-way branch out of each state and 2-way branch coming into each state. It's very simple to decode. How do you decode this code? Basically, you take your favorite trellis decoder, a Viterbi decoder or a BCJR decoder, and you go round and around in the circle until it converges. And in practice, it converges in 1.5 cycles, and performance is only about 0.1 dB worse than true maximum likelihood decoding. So you don't lose very much in performance, you gain a lot in complexity. Therefore, this is a better realization for decoding purposes of the Golay code than any of the cycle-free representations that I gave you. Yes, Tony?
With the issue of directionality, when they go around, somehow implicitly you choose to go clockwise or counterclockwise.
You can do either. It does not matter, right? But that's, how you might. It's all in the mind of the designer. How do you think about designing something? And sometimes it's helpful to impose an order on it. Okay, so that's
complexity versus time performance. What happens there? Or execution? What is actually the trade-off?
There are many fewer cycles involved in decoding this it's in the cyclic tail-biting form.
So it's better in terms of?
It's better in terms of number of decoding computations.
Than the cyclic?
Than the trellis. But if you take the cycle-free case, then you get an exact answer. You know you have the maximum likelihood decoding. In the other case, you simply have to do an experiment and you find, well, it isn't quite as good as maximum likelihood decoding. It's about 0.1 dB worse. But that's a trade-off you might well be willing to make. Okay, now this is an answer to Sasha's question. You've probably almost all heard about low-density parity check codes. These are capacity approaching codes that are today the principal class of capacity approaching codes. And they're based on a simple parity check realization. A code can be described as the kernel of a certain parity check matrix, HT. What do I mean by that? I mean this graphical representation I have down here. We have n bits in our code. In this representation, each of the bits is replicated by an equality constraint, so each of these is a copy of these n bits. The n bits have to satisfy n minus k parity checks. That's what this plus means. It's a parity check constraint. The mod 2 sum of these bits has to be equal to 0. If I impose n minus k such parity checks, then that's one way of defining a linear code of length n in a standard algebraic way. And this is what its graph looks like. Does this graph have cycles? Yes, almost always. And for any good code, it certainly does. And it's the cyclic structure of this that makes possible efficient decoding. The decoding of this is actually the individual steps in decoding are very simple, but again, it's an iterative decoding algorithm that keeps updating beliefs or likelihood guesses until it converges to something that it's happy with. And it's certainly not a maximum likelihood decoding algorithm. It's an iterative approximate decoding algorithm. Any questions on this? Because these are the kind of graphs ultimately we're going to be interested in.
And what's the performance again in this iteration?
You have to measure it.
How close it can come?
To capacity?
Well, not to capacity, to the maximum likelihood.
Well, there's a lot of analysis on this, and it depends on a lot of detail, but the practical result is that codes like this can get within tenths of a dB of capacity on it. So this, again, from an engineering point of view, is a real good solution. Okay, very basic concepts. I'm going to introduce trimness, which you're going to think is very obvious, as a predecessor to talking about properness, which I don't think is quite so obvious. So let's take a single constraint code C, a single vertex, and a single variable V involved in that constraint. We're going to say C is trim at V if the projection of C onto the alphabet of V is equal to all of V. In other words, all of the elements of this alphabet occur in at least one place in the constraint. Otherwise, that if it doesn't occur, then it's never going to be used. So it seems obvious that you should trim the alphabet down to the values that are actually being used. Here's a graphical picture of this projection. Just to introduce you to my notation, this is a dummy constraint, and this can be anything. All the rest of the variables in C can be anything. And then the question is, what can V be? And hopefully it's going to equal all the values in the alphabet. If it isn't, we may as well trim it. So it's quite obvious that you want all constraint codes to be trim at all variables. And again, going through in excruciating detail, suppose we had a constraint that was not trim at a certain variable V. How would you trim it? Or this first step, here's an equivalent realization involving a trimmed alphabet, which is the set of values that are actually used in that alphabet. And then to get something equal to the original constraint, we're going to define the trim constraint is the same as this, except it's going to use this alphabet rather than the original V. And then we'll put in an inclusion constraint here that's basically driven by V tilde. It says that V has to equal V tilde. That's the effect of this inclusion constraint. Cap V tilde being a subalphabet of V. All right, so that's an equivalent realization, and its graphical form. And now we'll show how a trimming operation actually works. If V is a state variable that is not trim, then there's a neighboring constraint, since all state variables of degree 2, that also involves V. Here's an equivalent realization. I take C and C prime, which originally were tied together like this, and I'm going to represent C by this equivalent realization with the inclusion constraint. And then I'm going to define C tilde prime as C prime with the inclusion constraint tucked into it. So that C tilde prime involves V tilde. And what does this say in here? This says just forget about, trim all values of V that are not in V tilde. So I'm going to get rid of them in the neighboring constraint. And I claim that the concatenation of C and C prime is equivalent to the concatenation of C tilde and C tilde prime. But now we have a state space that's only of size V tilde rather than a V. Elaborate way of proving that we can just assume that all constraints are trim at all state variables, because if they aren't trim, we can trim them by really adjusting the neighboring constraint in this way. All right, properness, much less appreciated but equally fundamental. So a similar definition, C is going to be, well, not so similar. C is defined to be proper at a variable V if the variables other than V determine the value of this variable. And in the linear group case, that means that if all the other variables are equal to 0, then V has to be equal to 0. And that will assure that this holds that this more general property holds. So how do we state that mathematically? We say the cross-section of C on V, which is defined as the set of all values of V that are compatible with 0 in all the other values. That's the definition of a cross-section. You set all the other variables equal to 0, and you take a cross-section of V with all the other variables set equal to 0. So that's a sub-alphabet of V. And so the cross-section has to be trivial, meaning there's no code word of C with a Hamming weight 1 in that place. All the other variables are 0 and that one's not 0. I think it's simpler to think of this in terms of this realization, where now I'm using the symbol of this as this is the constraint that all the other variables must equal to 0. All right, it's like a ground in electrical engineering terms. All right, and if all these variables are set to 0, then what can V be? That's the cross-section. All right, so this is a realization of the cross-section. So at first glance, I don't think it's so obvious that C should be proper at all variables, but there's a very nice duality theory here in this subject, which one of the easy results is that a constraint code is proper at a certain variable if its dual code is trim at the corresponding variable, which suggests that properness is as basic as trimness.
So what is the definition of duality here?
Well, this is based on projection cross-section duality, which is a basic duality principle.
What is the duality in the group case?
Same thing. It says.
So is there a pairing or something? Or what is it?
It's an elementary group theoretic result that says that it's the first thing I prove in this subject. It's in signal processing. It's the slice projection result. It holds at a very elementary level for finite abelian groups, or at any place where duality is well defined.
So you go to subgroup cosets and stuff like that in the group case?
It's not that complicated. It's very simple. It says precisely this, that if you have one subgroup of a direct product group, then it's dual. You have a dual code that's well defined. So this is a group code. This is its dual code. If I project the projection of this onto any subset or a certain value is the dual in the orthogonality sense of this. And so the dual of 0 is the whole space.
Okay.
All right, so that's the argument.
What's the hat here?
The dual space, or the dual group.
In principle, we could identify them, V and V hat, couldn't we?
In the linear, in the linear and finite abelian group case, they're certainly isomorphic, and So this is just to develop some general notation. In some topological group cases, they're not isomorphic.
Of course, once you go beyond finite, then
Right, circle group and the integers,
yes, exactly.
This sort of thing. All right. All right, so let me go through a couple of steps like I went through with trimness. Suppose it's not proper. That means the cross-section of C at some variable V is not trivial. Then I decompose C into the following equivalent realization. I decompose it into V hat, where V hat is the cosets of the cross-section in V. So this is a quotient group. I think some people have been scared away from this subject because they don't feel they know any group theory. This is really all the group theory you need to know is understand what a quotient group is. It's a set of cosets of CV in V. So that's a smaller alphabet when this is larger than 0. And then what is this constraint here between V and V hat? It's the natural map constraint that, let's take V as the input. Then V hat is constrained to be the coset that contains V, the coset of C. All right, so that's what I call a natural map constraint. So I hope you can see that this is equivalent to what I had previously whenever the cross-section is non-trivial. And so again, we get a local reduction result when we have a non-proper constraint code at V. Similarly, I can substitute, I take C, I take its neighboring constraint C prime that also involves V. So my original picture involves C, V, and C prime. Then I decompose C as I've just shown. Then I take this little thing and I shove it over to C prime to create C tilde prime. And so this over here is now a reduced code which has as an output V tilde, which is smaller than V. And what does this mean? This means that I have this quotient group as my state variable, and every value in here is mapped into its corresponding coset, and that's the output over here. So I've reduced the size of the state space without changing the implementation. It realizes the same code. So because I can always shove this over into the next constraint, I claim that without loss of generality we can conclude that all constraints are proper at all state variables. All right, so trimness and properness are two fundamental key properties. And one other fundamental group theory theorem. It's again very simple. Fundamental theorem of subdirect products. What's a subdirect product? If I have a direct product A cross B, a subdirect product is any subgroup of A cross direct product of A and B. All right, what is it? What can its structure possibly be? I'm not going to prove this. It's a simple proof using the correspondence theorem that Sasha will have seen by the time I finish saying this. The theorem is if I have such a subdirect product and I project C onto A and B, getting the projections, and let these be the cross sections onto A and B, then these three quotient groups are isomorphic. All right, and the proof is by the correspondence theorem. I will assert to you this is easy and fundamental, but I don't expect you to follow the proof in general, just Sasha. All right, so what does that say? Let me draw a picture of what that theorem says. The theorem says that here's a realization of any subdirect, of a generic subdirect product. What internally, I take the quotient of the projection of C onto A over the cross-section of C onto A, and similarly over here. And I introduce these two constraints, which I'm going to call interface nodes. And what are they? They're a combination of an inclusion constraint and a natural map constraint. So neither one is the input. You might think of this as being the constraint as we take only the values of A that occur in the projection of C on A, the ones that are actually used in C, and we putting them in here on this side with A, we map them through this natural map in the same way as I did in the proof I just gave you into its coset. Its coset of C cross-section A and C perp A, C projected on A. Okay, so it's the combination of an inclusion constraint on the projection of A onto C, and a natural map constraint from that projection onto the corresponding quotient group. Or you can do it in the opposite order, it doesn't matter, you get the same thing. So this is a complicated constraint, it's a behavioral constraint. It doesn't have a cause and effect structure. You can't say one side is the cause, the other is the effect. It simply says these two things have to be constrained in a certain way. And I call that an interface node. The middle one is an isomorphism. That's the isomorphism of the theorem. It says that these two quotient groups are isomorphic. Which implies the third isomorphism, and that's all there is to it. But this fundamental structure is what's going to prove all our theorems for us, or many of them. And just to drive home how fundamental this is, I want to make a few remarks on homomorphisms, which I hope that you all have encountered at some point. Think of it as a linear transformation if you don't know any group theory. Given a homomorphism from A to B, which has a certain kernel and a certain image, let's just say its graph is the set of all pairs that can occur, the all A and phi of A that can possibly occur. And you see that has the structure of a subdirect product. The first term is in A, and the second one is in the other alphabet B in the image space. In a homomorphism, we always require that the projection of C on A be A. In other words, that we can map from any element of A. And we also require that the cross-section of onto B is 0. In other words, if I put in 0 into the homomorphism, I've got to get 0 out. So those two are constrained, and this cross-section is the kernel, and this projection is the image of the homomorphism. So in a homomorphism, C is always, the graph is always trim at A and proper at B. And conversely, if we have a subdirect product which is trim at A and proper at B, then it's the image of a homomorphism. All right, according to our structure theorem, we can realize the graph of C using the structure theorem is possible as follows. We do the natural map of A to A mod the kernel of the homomorphism. And over here we have an inclusion map of the image inside the B, the range of the homomorphism. And the fundamental, according to the structure theorem, these two things are isomorphic, which is in fact the fundamental theory of theorem of homomorphisms. So this is in fact a corollary of the more general theorem that I gave you earlier, and I hope you were impressed, because anytime you can get the fundamental theory of homomorphisms as a corollary, you're having a good day. All right. So in a system theory context, I would ask, what is the difference between a homomorphism and a general subdirect product? A homomorphism has an input-output structure, all right? And this is what most of system theory is, has input-output structure. You have input A and it produces an output B. And the causality goes in this direction. And that's indicated by these arrows in the natural map and inclusion constraints. A subdirect product is more general. It's behavioral. It simply says there is some joint constraint on A and B which has a group structure or a linear system, a linear structure. And I think this illustrates very well why behavioral system theory is more general than input-output system theory. So I'm totally bought into that. All right, some consequences of this. Let's see, I'm going much slower than I expected, so I'll speed up a little bit. Take a single symbol in a length n group code and apply this reduction to it. I will get a picture like this. In other words, I reduce the symbol A to an effective variable alphabet, A tilde, by reducing it to the quotient that I've talked about, and put that into the code instead. I can always do this in view of the structure theorem. This is always has a size or a dimension less than or equal to the original one, and it's all I really need to go into the code. And now that I've done this, the code, I should say here, C tilde, is trim and proper at A tilde, and I've reduced the code to the form of what's I've called a coset code. It's a code over the cosets of the cross-section of C and A, and that's all you really need. And you can apply this to all the inputs and get this general canonical decomposition of any length n group code where you have these interface nodes that take care of all the non-trimness and the non-properness that there might be in the input alphabets. Those, by the way, we can't use our trick of pushing the interface node into the adjacent variable, because the adjacent variable is somehow outside the picture. This is an external variable. We can't change it. So we have to take it as it's given to us. And we can't do the trick we did with state variables of just moving it into the adjacent constraint, because there is no adjacent constraint for input variables. So we have to live with these interface nodes. But apart from the interface nodes, now we've got to a realization in which all the variables are internal. In fact, even these effective symbol variables are internal state variables, and therefore we can assume that all state variables in our realization, all variables in our realization, are trim and proper. So this decomposes any realization into a realization made up only of interface nodes and constraint nodes that are trim and proper.
So this is the same line of thinking where I take a system and I decompose it to fundamental components plus their interconnection.
Probably.
Like I do in finite automata, or except there I have inputs and outputs. And here you don't. You just look at
external variables in a
sets of
right.
variables, and then you can try to decompose it that way.
I expect it's a very similar decomposition. Okay, fragments of realizations. These are definitions. A fragment of a realization is what you think. You cut out a certain part of the realization, and you consider only a fragment. Internally, you can think of a fragment as being a realization of its external behavior. Its external behavior is like a generalized constraint. A leaf fragment is one that you get from cutting just a single internal variable, a single edge in the graphical picture. And so that gives us a leaf fragment. Another definition for fragments is cycle-free, and we say a fragment is cycle-free if it has no internal cycles. We say it's internally trim and proper if all of its component constraints are trim and proper at all their variables. Then it turns out that for a cycle-free fragment, it's trim and proper at all its external variables on its boundary. Let's consider the combination of these two, a cycle-free leaf fragment, which in graph theory is called a rooted tree, with the root being at this single state space or internal variable S, J. So we get, by putting all these things together, if we have a cycle-free leaf fragment that is internally trim and proper, then we know what its external state space is isomorphic to. It's this quotient of the projection of the aggregate of all its external variables over the cross-section of its external behavior with respect to all these variables. So we get this very simple resulting picture consisting of an interface node and isomorphism of any cycle-free leaf fragment. From that, we get a wonderful general theorem about minimal cycle-free realizations, which will show that there is an essentially unique minimal cycle-free realization, and it depends on very little. It depends only on local properties. So if I have a cycle-free realization, I know from elementary graph theory that if I cut any edge, that's going to be a cut set. I'm going to cut it into two parts, each part being a cycle-free leaf fragment, as depicted down here. I've cut at Sj. So two rooted trees with a common root. So suppose the whole graph started out being internally trim and proper, the whole realization. Then, from the previous theorem, every state space is isomorphic to a certain quotient group defined on one half of it, which I might call the past, and also to another quotient group on another half of it in the future. And moreover, S is minimal. And here's the proof. I've already shown that this is an equivalent realization of each of the cycle-free leaf fragments tied together at Sj. Therefore, Sj must be isomorphic to both of these things. In fact, since this is a realization, this shows me that the code is the set of all pairs of past and future components that are in corresponding cosets. So that's a realization with only a number of states equal to the number of such cosets, which I can measure either on the past or the future. And furthermore, it says that if the two halves in past and future are not on corresponding cosets, then they're not part of the code. That means I can't reduce the number of states. So this is the minimal number of states that I could possibly have. This is a fundamental result that's been known a long time from Willem's system theory and probably before that. But I think this is a remarkably simple way to prove it. I already showed you that in order for something to be minimal, it had to be trim and proper, because I showed you how to reduce any realization that's not trim and proper. So therefore, we get the following theorem, which I believe was first published in my paper with Heidi, which is the following are equivalent. If a realization is internally trim and proper, that simply means locally all the constraints are trim and proper. Very, very simple condition on each of the constraints. Then, well, this is stated differently, but then every state space is isomorphic to either of these two quotient groups. And furthermore, every state space is minimal, meaning the whole realization is minimal. And going the other direction, if you have that, then that implies the top line.
All groups are abelian here, right? All groups are abelian.
All groups are abelian, yes. Yes, haven't considered non-abelian. All right, so again, that's an extension to general cycle-free graphs of a result that's been well known for conventional state space system that's on a chain time axis. Now I have 5 minutes to go. I'll take 10. Let me skip this one. That essentially settles the cycle-free case. All right. Once we've what it hasn't settled is what graph we're going to try to realize our code on. And I showed you for the GoLay code, there are many different possibilities and probably some we haven't thought of yet. But if you choose a cycle-free graph, once you've chosen it, then everything else a minimal realization is determined, and it is easy to compute. How do you compute it, by the way? You can do it all locally by if any of these constraint codes is not trim and proper, you just go through the process of making it trim and proper that I've already outlined to you. And once you've done that for all of them, you're finished. So for these graphs, as I've said, they're easy to decode, but the complexity is necessarily high, and there's some results that are almost conclusive that say if you have a capacity approaching code, then the complexity of any cycle-free realization has to go up exponentially. So to get to capacity, we're going to need realizations with cycles where the minimal realizations are not unique, where the decoding algorithms are iterative and approximate, but in fact, this is the way we go. Now, as a first step into cyclic graphs, I have a little structure result having to do with the two-core of a graph. If you have a graph realization or a graph, the two-core is the maximal connected subgraph such that all vertices have degree greater than or equal to 2. In other words, there are no isolated nodes and no leaves. And how do you get such a graph? You simply peel away all the leaves one by one till you down to the two-core. Now there must be another name for two-core. Does anybody know? I've been searching. Anyone know from graph theory? All right, nobody knows. You would think such a fundamental concept would have a better name. So take any graph, and it has a cyclic part consisting of its two-core, and then it has cycle-free leaf fragments that are attached to the two-core, like this. So that means any graph of a code can be decomposed in this way, in which we already know how to deal with all these cycle-free leaf fragments. We can get minimal realizations of all of them. We can decode them in a non-iterative way. We can do iterative exact decoding to produce something which then goes into the two-core. So all of the complexity is now isolated to the two-core. And I guess the only practical consequence of this is that we can, without loss of generality, assume that a cyclic graph has no leaves.
So the C tilde is the core here?
C tilde is the core, right.
Okay.
All right, so we've simply reduced our problem to a leafless problem. Okay, internal, external behavior of fragments. I'm not going to introduce all this notation, just in terms of pictures. The internal behavior is defined generically as follows. Here are my external variables. Here are my external or boundary state spaces. Here are my internal state variables. Each of these appears twice. Each of these appears once. Each of these appears once. This is the set of all the constraints, and all of these values must satisfy all these constraints. So this is an aggregate picture of everything in vector space terms. And there's one further set of constraints that have to be satisfied. S has to equal S prime for each of the internal variables. All right, that's the edge constraint. So that's an equality constraint. And here is therefore a realization of the internal behavior. If I want to get the external behavior, then I project on just to the external variables, both symbol and state, by putting an open constraint here or just deleting it altogether. All right, so that's my generic picture. There's a beautiful duality theorem that I haven't emphasized today, but really I take as a starting point for all this work. If we dualize the picture, and how do we dualize it? We replace each symbol alphabet by its dual alphabet, which in the vector space case is a dual vector space. Typically it's, f to the n is dual is also f to the n, or if it's a finite abelian group, the dual group is its character group. In both cases, in the finite abelian group case, we get that the dual alphabet is isomorphic to the primal alphabet, so it's just purely notation to put the hat over them to keep them separate. Similarly, replace each state alphabet by its dual alphabet. Replace each constraint code by its orthogonal code. For instance, if we have an equality constraint, its orthogonal constraint is a parity check constraint, single parity check constraint. And final little thing that gets in the way is we have to invert the sign of one of each pair of state variables. And that's why this theorem wasn't discovered long ago. There's this very nice theorem from my 2001 paper. If you just do this, make all these local substitutions on a realization, and on a realization that realized C, you will get a realization of the orthogonal or dual code C perp.
What do you mean by changing the sign of the pair?
Here, I'll show you. Okay, so what does that say? Here's a generic realization of a fragment on the left, just as I showed you before, except I've taken away this variable as I may. What's its dual fragment? I replace everything by its dual variable, and all of these constraints I replace by their orthogonal constraints. And what is the orthogonal constraint to a 2-input equality constraint? It's a 2-input inversion constraint. So here the constraint is that S hat prime has to equal minus S for each thing. Or in other words, there's a sign inverter in the middle of every edge.
Or whatever the minus is in the group that gets, right?
The minus of the group. These are all additive groups, yeah. All right, and if I do that,
In binary, you don't need to do anything.
in binary, you don't need to do anything, right? That's why we love binary. Okay, a little bit on observability and controllability, because I know John and those of you who are interested in system theory will be interested in this. A fragment generically is observable if somehow its internal or state variables are determined by external observation. First note is that we have two possible concepts of observability here. One is that the external variables, we may ask whether it determines the external states. That's the kind of question that would be appropriate to a constraint. To a realization, a more appropriate question is, do all of the external variables determine the internal state variables? So that's more like the observability of system theory. So we come up with observability tests, basically asking whether the kernel of certain homomorphisms is trivial or not. And here's a test for external observability. Here's a realization of it. You simply realize this SFX by setting all the variables to 0, but allowing any internal variables you like. And you ask whether this is trivial or not, and that determines whether it's observable, just by definition, really. Internal observability, you set the external variables to 0, and you ask if the internal variables are 0. Nothing new here. Controllable, the tactic that I've taken is simply to define controllability not as the dual of observability, which would be too easy, but to find an appropriate definition for controllability such that I can then prove that it's the dual of observability. Okay, and in these two cases, I get two different concepts. All right, so external controllability, corresponding to the first of those definitions, is if the projection, the dual concept would be if the projection of B onto the external behavior is surjective, if all possible external state configurations can occur. So for a leaf fragment, that amounts to simply being trim, same as the definition of trim. For a trellis fragment, the one you're most used to in conventional linear system theory, this corresponds to JK controllability. Can all possible pairs of states at the beginning and end of a trellis section occur? So that's what this notion of controllability goes to. Here's a realization of a certain, here's a realization of a certain test variable here, which if it's complete, then we're controllable. This is, in fact, generating the external variable. And here the proof is we just observe that this is the dual realization to what we have earlier. So F is externally controllable if and only if F naught is externally observable. Internal controllability we do in a different way. The internal behavior is really set by two sets of constraints. One is the set of all our constraint codes, and the other is the requirement that the two versions of each internal state have to be equal because they're tied together by an edge. So the internal behavior is the orthogonal space. It's determined by two sets of checks. One, the orthogonal parity checks, and the other this validity check that S hat must be minus S hat prime. That's one way of determining that S equals S prime is if it's orthogonal to that. And F is internally controllable if these two check spaces are independent. Their intersection is trivial. And from that you can easily prove that it's the duality, it's the dual of internal observability. But I think it's the right way to define this kind of controllability. We get a controllability test that is the dual of the observability test. All right, so that's the concepts, two different concepts of controllability and observability, and the showing that they're dual. We can show that unobservability and uncontrollability basically all occur within the two core of your realization. If you don't have cycles, you can't have it once you've established trimness. Trimness and properness are kind of a very elementary form of uncontrollability and unobservability. So that's the only kind you can have in the cycle-free part. You get rid of that, you have a minimal realization. So this is a more general thing that can only occur when you have cycles. Here's some examples which I think will show you how similar this is to classical linear system theory. Very simple linear tail-biting trellis realizations for which we can draw traditional trellis diagrams with the additional constraint that the final state has to equal the initial state. So that's implicit in these diagrams. Here's an example of an unobservable realization. Every transition is simply the same. And as you can see, there is a cycle of all zeros other than the zero cycle. Or in other words, every possible code word is realized twice, so it's unobservable. All right, so that's what unobservability looks like. The dual of this realization is this tail-biting realization, where there are only two cycles and they're completely disconnected. You will all recognize how this looks like traditional systems on the bi-infinite time axis. Here's how the controllability test works. You simply count dimensions, and this is more general. If this is showing you how to reduce an unobservable or uncontrollable realization, you can pinch, in the unobservable case, you can pinch the state space at one place, and that will reduce it. In the controllable case, you merge it at one time, and that will reduce it. However, this to me is interesting because this doesn't work for group realizations. This works fine for linear realizations, but it doesn't work in general for group realizations. And so that's a very interesting open research question. What's going on there? And how can we get a similar reduction for the group case? So we've proved that this, for tail-biting linear realizations, that they're uncontrollable if and only if their behavior is disconnected in the way I showed you before. Here's a more complicated example. Unobservable and its dual uncontrollable. And again, this is for tail biting. We'd like to extend this result to general graphs. And we haven't pinned down what the relations are between these tail biting notions of controllability and observability and the traditional codes over the integer time axis. We've had an interesting discussion about uncontrollability. It's clear that unobservability is not something you want in a code for decoding, because every code word is represented by multiple representations, and the decoder could settle on either one or oscillate between them, and so it's really hard to see how unobservability could be helpful. So we want to get rid of that in any code we're going to use. But maybe we don't have a similar simple hand-waving argument for uncontrollability. And we have actual examples where people have used uncontrollable realizations, which you might think would be bad just by the name of it, and they work better. In low-density parity check codes, for instance, people have sometimes used some redundant parity checks. So now a parity check realization is controllable if and only if the parity checks are non-redundant. So when you add redundancy, you add controllability. And sometimes this is done deliberately, sometimes just fortuitous. It's part of the construction. Nobody really thought about it. Seems to work fine. But so is there some more systematic way of exploiting uncontrollability or redundancy in low-density parity check codes and more generally? And when I gave an earlier version of this talk at Allerton, John piped up and said, gee, in control systems, we sometimes do introduce a little uncontrollability very carefully for robustness. And I suspect the same thing is probably true of in coding. But certainly no one has picked up this ball and run with it yet. So this is another question that I think would be useful and gets us a little bit closer to practical questions. All right, so this is my summary slide. Thank you for sticking with me past noon. I and Heidi, more me than Heidi right now, continue to push along at this, along with a couple of other people. So we're not quite finished a complete development of this theory. We have a strong indication that you don't need to consider constraint codes of degree any larger than 3, cubic constraint codes. But we don't have a good general theory for degree 3 realizations yet. We do for trellis realizations, which is a particular form of a cubic realization. And it has to be admitted that we don't have a very good connection to the actual engineering analysis of codes and decoders. This is all just system theory, and apart from the previous slide, I haven't really told you, well, apart from the cycle-free versus cyclic case, which was already known, we don't really know what graph structures yield good performance. This question of carefully designing uncontrollability, what would you take into account? Decoding performance analysis, it's well known that there are decoding performance analysis, it's helpful to look at extensions of your original graph covers. That's what determines the pseudocode words, which, since our decoding algorithm is local, are perfectly valid from the point of view of the decoder. Pascal von Tobel and I have got some initial work looking in this area, but certainly 99% remains to be done. So those are the research problems I can offer to you. Thank you very much.
Thank you.
And
So we have time for a couple of questions. Anybody?
And I understand I'm going to be back up here at 2 o'clock if we don't cover all your questions now.
Brief David more. They will be very interesting topic for several of us who have done algebraic system theory of all kinds.
Yeah, do you want to make any comments, John?
Well, very simple example. If you're trying to control something on a restricted manifold, you don't want to have controllability in the direction of our restriction. So if I want to be on a sphere, I don't want controllability this way. So if you look at it that way, then it's useless.
You mean it's a don't care or it's positively harmless, harmful?
No, you don't want to have it, period.
It's harmful.
It's harmful.
Yeah.
If you're interested in circuit implementations, then it becomes more serious, because non-minimality is not good, because non-minimality measures dimensions of states, but it doesn't measure robustness in the sense of transforming things from numbers to actual circuit elements. That's well known to classical network theory, which we don't teach anymore, but anyway. Benefit synthesis and sections and all that stuff, right? If you look at these networks, they are very non-minimal, but they are very stable in terms of getting the parameters from numbers to the circuits. What's the output of that coding? So my question to you is this: how much coders or coding theory people should care about the hardware where the code is going to be realized?
Traditionally, we don't care because everything's discrete. And
But you should, because it's not fault-free, even if it's discrete. No circuit is fault-free.
okay, well,
In other words, is there a notion of robustness and where it's coming from?
to my knowledge, there's been a little work on low-density parity check decoding on circuits that may have faults in them. But of course, it's a very narrow stream. And
Because I'm thinking if there's going to be any serious connection, it's going to have to come up from this thinking.
Okay.
Is there a robustness notion in coding, then I may understand why you're getting results like where if you have non-controllability, it helps you and so on.
okay, I would be more interested just in getting somebody who is deeply knowledgeable in everything that's been done in system theory and control theory traditionally to really get deeply engaged in this and seeing what parts are well known or somewhat known or
Additionally, you won't get it because it doesn't require the limit of out-of-box thinking in system theory. There is these papers I sent you from Malcolm Smith.
Okay.
This very mechanical systems with the analog of capacitors, they are converters. All of them are non-minimal. Right?
Okay.
For good reason.
Robustness mean in the coding sense? Okay, robustness resistance is well defined. So,
Is it?
well, I mean, there are
Parametric.
definitions. There are.
No, but here the difficulty is that robustness will have to be structural robustness. And in
that's my
systems, we
question.
don't understand.
No, robustness means things like avoiding traps in your iterative decoding, speed of convergence. These are the kinds of things that are helped by having redundant parity checks, which is uncontrollability. So it's all still in a perfectly discrete world, but we have this iterative decoding algorithm, and it has fragility.
Yeah. Any other questions? I have a little bit of still confusion in my mind as far as this external observability and external controllability case. Let me ask the question. If it's stupid, it's stupid. Okay. We worry sometimes in controls of something which is called output tracking. In other words, I want to be able to have some input that I can go to many segments of output. Is that related to external controllability? In other words, I don't want to do it through the state space. I want to just look at the input output, and I can say, if I put segments of inputs, I want you to guarantee me that certain trajectories or certain traces will all be covered. I want to do it through the state space.
I'd have to think about it. That's not clear to me just
I don't
standing here.
understand exactly the analogy. Do you understand the analogy with external controllability? I don't. Because we have functional controllability and things like that
Yeah.
we do in controls, but I cannot connect it to this external controllability.
Well, I think there are probably more than two notions of controllability. So,
There are. Control theory and in traditional control, especially in aerospace, there are.
right. So,
But I don't know how to connect it with what you have here.
it's,
Any other question? Okay, let's take the speaker again. And 2 o'clock here, if you want to come, please come.